n and get 1 minus 1/4 z plus d to the inverse plus w. And what I'm doing now is applicable to a general operator, not as to replace Laplace. Yeah. So it equals 1 if m equals n equals 0, 0 otherwise. But then the same thing is saying that it's the coefficient of z to the power 0, w to the power 0, the so-called constant term in z to the n, w to the n. But z to the power n, w to the n is a basis. So this means for any Lorentz polynomial, little p of zw. But this is what's called an ideal. All the Lorentz polynomials that are multiples of this polynomial, there's some other Lorentz polynomial, constitute a sub-vector space. And we all know from linear algebra, if an operator, a linear functional is defined on a subspace of the vector space, you can always find, you can extend it to the whole space. And if you still don't like that it's an infinite dimensional vector space, and I don't like it, there's also a way to get around it. You truncate it to all the Lorentz polynomials of degree less than blah blah blah, and then it's nested, and you prove it for each of the finite versions, and then you prove it's consistent, like in formal power series. And I believe that lots of so-called, maybe all of so-called infinitary mathematics can be resolved in this way. But this is basically Leon's idea, except in the continuous context, you have to invoke Han-Banach. This basically tells you can always extend a linear functional in a topological vector space, and you have to worry about topology and all this nonsense. So I believe that this is really the best way to do it. I'm very glad that Zim Lepalsky is here, because after I did this, I realized there's yet another way to prove that there's always a fundamental solution of any discrete difference, any partial difference equations. So let me do it a la Lepalsky. And this has an advantage. There is not only existence, it actually constructs it. So it uses formal power series. So formal power series have been used very much in combinatorics, but people could not handle negative powers. So let's look at the easy case to get a fundamental solution of this discrete difference equation. You take the formal power series, sigma f of m. So, and in this case, there may be, you're looking for a solution that only defined on the positive quadrants. Positive quadrants. So call it f of zw. This means that 1 minus z minus w times f of zw equals 1. So you can do the simple algebra and then do Taylor expansion. And Maple can do it very well, although in this case you don't even need Maple. And you get the binomial, the Pascal's triangle. So you can always construct such a fundamental solution. So 1, 1, 1, 2, 1, 1, 3, 3. It's basically Pascal's triangle this way. That's a fundamental solution for this operator. But things get more complicated when you have all around when the symbol is not so simple, but like in the Laplacian, 4 minus z plus 1 over z plus w plus 1 over w.